Okay.
Yep, you should be started.
Okay, perfect. Thank you very much. Right. So hello, everyone, and welcome. Thank you for joining this webinar, which is hosted by the UK and Ireland Power and Energy Society chapter. I'm Panagiotis Papadopoulos. I'm the chair of this committee, and I'm co-hosting this event with Gian Ingley, the vice chair, and Eduardo Dike, the secretary and communication officer of our committee. So we're very excited to host Professor Rahman, who will be talking about the global electric power sector engaging with environmental issues. The talk is going to take roughly around 45 minutes, if I'm not mistaken, and there will be time for 10-15 minutes after that for questions. You can use a chat box to place any questions, and you can also, I think you can raise your hand if you want. We can unmute you basically to talk if you want to say something. Before we begin, a short introduction for the speaker. So Professor Saifur Rahman is the founding director of the Advanced Research Institute at Virginia Tech in USA, where he is a Joseph Loring Professor of Electrical and Computer Engineering. He also directs the Center for Energy in the Global Environment. He's a life fellow of the IEEE and an IEEE Millennium Medal winner. He was the president of the IEEE Power and Energy Society for 2018 and 2019. He was the founding editor-in-chief of the IEEE Electrification magazine and the IEEE Transactions on Sustainable Energy. He has published over 140 journal papers and has made over 400 conference and invited presentations. In 2016, he served on the IEEE Board of Directors as the Vice President for Publication. He's a distinguished lecturer of the IEEE Power and Energy Society and has lectured on renewable energy, energy efficiency, smart grid, energy internet, blockchain, Internet of Things, sensor integration, and various other topics in over 30 countries. He's the founder of BEM Controls, a Virginia-based software company providing building energy management solutions. He served as the chair of the US National Science Foundation Advisory Committee for International Science and Engineering from 2010 to 2013. He has conducted several energy efficiency, blockchain, and sensor integration projects for Duke Energy, Tokyo Electric Power Company, the US National Science Foundation, the US Department of Defense, the US Department of Energy, and the state of Virginia. And he has a PhD in electrical engineering from Virginia Tech. This is a very long list and impressive bio from Professor Rahman. I would also like to mention that Professor Rahman is a candidate for IEEE President-elect for this year. So you can find some information on the chat box as well, and the website, the personal website of Professor Rahman as well. So enough with me. Professor Rahman, the floor is yours. We're happy to listen to you.
Thank you, Panos. Let me share my screen first. I appreciate the kind introduction, and I can see a lot of familiar names on the screen. I appreciate all of you taking the time to join this event. I hope you'll find the content interesting. So this, as Panos said, focusing on global electric power and show how the power industry is transforming so that we don't contribute as much CO2 as we used to in the past. So we are playing good citizens' role in this debate of climate change, global warming. Now let's talk about history first, where things are happening and what are the fuel contributions to global warming. So if you look at, first of all, left-hand side of the screen, production of electricity from different fuel sources globally. So 2017, things are not changing much. 2017, 38% of electricity globally came from coal. Globally, 38%. I'll give you a number later on, some top countries on this list. Next was natural gas, about 23%. Number 4 was hydro, 16, nuclear 10. Solar, wind are small, under 5%. That's the overview of 2019 number here. On the right-hand side, you see countries which are the top 10 countries, highest consumer of electricity as a whole, not just coal-based, overall. The China number 1, which is a, very large number, Chinese number in the year 2017 was about 5 5,500 trillion watt hour, big number. Followed by US, under 4,000 terawatt hour. India, Japan, quite a bit less. But India, Japan are pretty close, about 100, about 1,000. All the way to Brazil, then France, US, sorry, UK on this list because UK is less than top 10 countries. Fine. Now the issue is, if that is the case, what is the overall layout? So again, this is the same data in a graphical format. You see China and US are the two dark green or black pictures. Rest UK in the light green, in third ranked in this case. So this is the global situation, UK 334, you can see at the bottom of the screen. Now, this is an interesting topic. We know coal is the biggest CO2 emitter in the world. So what is the coal generation happening? 75% of the global demand for coal comes from Asian countries. If you see the screen on the left-hand side, China is about 2 billion tons of coal used per year in 2018 data. Followed by India, about 0.3 billion, 0.4 billion. The rest of Asia Pacific, that's Australia, Indonesia, Malaysia, Korea, and all that. And the rest of the world is below 1 billion. So out of almost 4 billion, 75% comes from Asian countries. That's the fact, history. On the right-hand side, interesting data. This shows the new contracts for coal power plant construction, new contracts, investments. You see, 2010, investment was made for 100 gigawatt of coal. What does it mean? That means their contract signed in 2010 to build 100 plants, each 1,000 megawatt each. Big number. That has constantly gone down to the tune 2018, about 22 gigawatt from 100 gigawatt, which is a good sign. So less and less of new coal is going into operation. This one shows, let's focus on the left-hand side of the screen first. Total CO2 emission as of 2016 from the top 20 countries, total CO2. This is China number 1, 9 billion tons. US number 2, 4.8, India 3, Russia 4, and so on. UK number 16, France number 20. France is less because France electricity comes mainly from nuclear in France. UK also building nuclear plant, but it's a political issue now. Things may not go as fast as we thought. So if I look at this list of 20 countries, these are total emission for the whole country. The big countries like India, China, say our numbers are higher, but you got a lot of people as well. So you should count not the total absolute for the whole country, count for number of persons in the country. It will be CO2 emission per capita. I'll get to that on the next slide. Just remember the fact here, China was number 1, Saudi Arabia was number 10 in terms of total emission. China 1, Saudi 10. Keep that in mind. On the right-hand side, looking at the share of CO2 emission country by country. China the highest, 29%, US 16, India 7, Russia and Korea, all of them are under 5%. That's the country's contribution, UK 1%. UK got rid of the coal plants, mainly replaced with gas. That's why the CO2 emission is less. Again, China number 1, Saudi number 10. Look at this. The per capita, Saudi becomes number 1 because number of people is much less, obviously, and they're a big oil producing country. When you produce oil, you refine it, you ship it, you mine it, and that produces CO2. That's why Saudi numbers are so high. Australia was nowhere in the top 10. Now they're number 2, US number 3, China number 4, sorry, Canada number 4. China became number 12. It was number 1. India became number 20. They're number 4 at the time. So this is the difference if you calculate per capita. This is a big debate globally. China, India says don't count the whole thing. A lot of people count per person. So this is the data per person. Good. Now, let's look at the overall CO2 emission from fossil fuel combustion, including industrial processes like cement manufacturing, not power only, cement manufacturing, things of a steel mill running on coal. So China, number one, 30%, US 2, 15%, EU 9%, India 7. The rest are very small. Fine. Now the question is, we showed you what is the total fuel usage for energy. Now we are showing emission from fuel combustion fuel combustion. Before, for electricity, we use only 3.3% of oil. Now globally, oil is responsible for 34.8% of CO2. How come the number went up from 3.3 to 34? Because that was only for electricity. Now overall, that means the big number is coming from transportation sector, obviously. Oil may include diesel and liquid fuel. Natural gas, 20%. That's the overall. Then the question comes back, which part of the world is contributing more and more CO2 emission? OECD, most of Europe, US, Canada, Japan, Singapore, the developed countries, they are about 36% responsible for global CO2 emission in 2016. The number has not changed much. China, 28%. Other countries, non-OECD Asia, if you forget Japan, Korea, and Singapore, 4%. That includes India. Africa, small, 3.6%. Fine. Then the question is Europe. What are the sources of emission in Europe for CO2? Look at that. Energy production, 31%. Manufacturing, 22%. Household, as your building, heating, cooling, lighting, air conditioning, all that. Transportation, 12%. Others are very small. This is a European scenario. Energy is the biggest contributor to CO2 in the European context. Very interesting slide. We showed China is big on coal. Look at that number. 2001, 73.4% of electricity in China came from thermal, meaning coal, mainly coal, some oil. Only 25.5% came from hydro, solar, and wind. Remaining came from nuclear. By 2016, the contribution from renewable went up from 25 to 33.8, and thermal went down accordingly. 2018, there was 37% renewables. 2030 target is 52%. That means more than half of electricity in China in 10 years will come from non-coal sources. So 52% renewable, 42% thermal, remaining 6% nuclear. That's fine. So this is the target for 2030. Now the question is, where is the emission coming from, CO2 emissions? Back in year 2000, 33% or 1/3 came from electric power plants. Another third came from transportation. 20% came from direct industrial use, like coal in steel mills, for example. And residential commercial, meaning heating in buildings, not using electricity, by the way, is using, in my office building, uses gas to heat, for example. Many homes use oil to heat. Korea have seen use coal to heat buildings. So this is the global distribution of anthropogenic, meaning man-made CO2. Much more CO2 is produced by the oceans, but they're absorbed in the ocean as well. So that doesn't count. Okay, if you look at the number today, 20 years from 2000, the electric power plant number has gone down to 26, 27% from 33%. Transportation has gone to almost 40%. This is the challenge. We in the power industry are replacing coal-based power plants to produce electricity from cleaner sources, but the transportation sector is growing, obviously, and then burning more petroleum, so their contribution goes up. We need to deal with that as we go forward. Now the question is, what other gases are causing or can cause global warming? These are called greenhouse gases. CO2 is the most well-known. Other 5 are methane, nitrous oxide, hydrofluorocarbons, perfluorocarbons, and sulfur hexafluoride. Those of us in the power industry know we use SF6 for substations in contained spaces like underground or indoor substations, SF6. If we look at the bottom of the screen, 1997, the global production of CO2 was 30 billion tons from fossil fuels and cement production, 30 billion tons. 21 years later, 2018, that has gone to 41 billion tons. 1/3 increase in 21 years. 2020 data is not here yet, but that number will be low 40s today. Now, very interesting data. We talk about these 6 global warming gases. How potent are these gases for their global warming potential? You can see carbon dioxide is my reference. If that's one, methane 28, nitrous oxide coming from natural gas primarily, 265, hydrofluorocarbons 138, per fluorocarbon 6,630, and a sulfur hexafluoride SF6 23,500 times potent compared to CO2. That means you got to be very careful where the CO2 SF6 is released. What this means, 1 ton of SF6 has the global warming potential of 23,500 tons of CO2. Big deal. Then the question is, how are they distributed? Well, look at this picture. Even though CO2 is small, but there's so much of it, if I take into account the concentrations, I see this number. CO2 today responsible, 5 years ago, responsible for 76% of 3/4 of the global greenhouse gas emission. Global greenhouse meaning all kinds, all 6. Next is methane, followed by nitrous oxide, 6%, and the other 3, HFC, perfluorocarbon, SF6, only 2%. That person is growing somewhat, but not a whole lot. But methane is also growing. Now the question is, where is the methane coming from? Well, if you look at US numbers now for greenhouse gas emissions, globally was 75%, US 82%. Global warming from natural gas, carbon dioxide from all sources, not natural gas, all sources. Methane 10%, then nitrous oxide 6%, this perfluorocarbon and HFC about 3%. That's US. Now the question is, fine, now we know methane is the 2nd highest contributor of global warming gas. Where is methane coming from? We know CO2 comes from transportation, from power plants, all of that. Methane comes from natural wetlands, meaning if you have vegetation that is flooded, it rots. When vegetation rots, it gives off methane, number 1. Paddy rice fields, very common. Paddy is grown in submerged water, and part of that is underwater. Emission from livestock production systems, that's your cows and goat and all the other livestock. They discharge a lot of emission, a lot of methane. Biomass burning, including forest fires. When you burn biomass has methane built in, that gets released. Number 5, anaerobic decomposition of organic waste. The garbage that picks up from your street, thrown into a garbage dump, that rots there, the organic material, and makes methane. In fact, there are power plants which are tapping into the garbage dump, picking up the methane and run the power station. It's possible. Also, when you drill for oil, you've seen pictures, I'm sure you have seen that. You drill for oil, you hit natural gas first. The gas comes out. What do? You burn it. If you don't burn it, you let it go into the sky. That's not good because they are not economically, I guess, advantageous to capture it and ship it. So they just let it burn or go to the sky. Good. Now the issue is, how potent are these gases for global warming? Well, look, 3 fuels: gas, oil, and coal, and then look at what are they producing: NOx, nitrogen oxide, sulfur dioxide, and CO2. We know CO2 is a global warming gas, so is NOx. SO2 is not, sulfur dioxide, not a global gas. It causes acid rain. If you mix SO2 with H2O, water, you make sulfuric acid, literally. That's why we call it acid rain. Gas is responsible for power industry now. 2.32 grams of NOx per kWh, kilowatt hour. Okay? Producing only 0.004 grams of SO2 per kWh. Very small. That's why gas is a clean fuel. Carbon dioxide from gas-based power station, 490 grams per kWh. That's gas. Oil number is, NOx is about the same, 2. SO2 is much higher. Oil has more sulfur. CO2, 781, about 3/4 kilogram of CO2 per kWh of electricity. Last is coal, 3.5 grams of NOx, 9.26 grams of SO2. That is why it has been called the acid-producing fuel, coal. And then, of course, it's a significant contributor to CO2, 1,090 grams per kilowatt hour. That means if you leave a 100-watt light bulb on by mistake overnight, 10 hours, 100 times 10 is 1,000 watt hour, 1 kilowatt hour. That means you help to produce 1 kilogram of CO2 just because you forgot to turn the light off, if it's a coal-fired generation. Just keep that thought in mind as you go forward. Now the issue with hydroelectricity. Yes, hydro is renewable. Is it clean? Clean meaning, is it green? I think not. Because hydropower plants contribute significantly in the part of methane production. How does it work? When you build a dam, by definition, you flood land behind it. The land was green, otherwise there's no water. Water means green. It's not, you don't build this hydro in a desert location. As the dam is built, the dam is holding water behind it, and the water is submerging all the vegetation that was there. All the vegetation will rot over time and release methane, goes into the atmosphere. But it's a one-time thing that happens first time you build the dam and submerge it. Next year, you're not flooding any new land, it's okay. However, there is a seasonal variation. Why seasonal? The dry season, the water level in the reservoir behind the dam decreases. Evaporation and many other things, they decrease. As they decrease, it exposes more land to the atmosphere. That means that land behind the dam, you see on the left-hand side of your screen, will grow new vegetation. As the rainy season comes, water level goes up, that new vegetation will be submerged and rot again. They'll produce some methane. That is an annual event. That's why we say hydro is not totally clean. What are the big countries in the world that is submerging a lot of land because of the dam construction activities? Russia is number one, 7.96 million hectares of land, or 20 million acres of land has been submerged in Russia because of dam construction. Second highest is US, 6.98 million hectares. Third is Canada, 6.5 million. China, number 4, 5.8 million. India, number 5, 4.5, 4.6, almost million hectares. And Brazil, number 4, 4 million hectares. This is the list of countries, a lot of hydro activities, and they're producing methane in some form. Look at these numbers. We know the first one. That is 1,090 grams of CO2 will be released per kWh of electricity. CO2, we know that fine. You look at the hydro base, hydro does not produce CO2, we know that. It produces methane. But if you look at the CO2 as your currency, it compares CO2 level. So each kWh of hydro-based electricity releases 225 grams of CO2. Coal was 1090, hydro is 225. It's not small, about a quarter. Other question is, where is the CO2 coming from when you burn gasoline? How much is it? Again, some simple numbers. If you burn 1 liter of gasoline in your car, 1 liter, you have helped to produce 3 kilograms of CO2. in that car. So that means, I don't know, your car may go 20 kilometers per liter of gasoline. So 20 kilometers you're driving, producing 3 kg. So about 3 over 20, so 0.15, 150 grams of CO2, 150 grams of CO2 you're releasing per kilometer driven. It's not small, builds up. This is the hydroelectricity situation. Now the question is, these are the problems. How do you solve the problem? Well, one simple answer is use less electricity. You use less electricity, you burn less fuel. We get that. Or you make your system more efficient so that you'll use less fuel to produce electricity that you are using. Make it more efficient, meaning your fuel consumption per kWh is less. Example, if you are burning coal today to produce electricity, coal is about 40 or 42% efficient. The more advanced ones, 42% advanced ones. Compare that with combined cycle power plant, usually gas driven. Those are low 60s, 62, 63%. That's an example of using less fuel to make same amount of electricity. Of course, third is obvious option, use more renewables and nuclear and see what are we doing globally. Okay, now this example shows you the top 10 countries in the world which have the highest amounts of renewable, meaning hydro, solar, wind, geothermal, bioenergy. But other things are small, even on the right-hand side of the screen. 2018 data, if you look at the global consumption of these fuels, which is wind, PV, and hydro is about half of it, 47.9%. Onshore wind, 23%. Offshore, solar is 20%. That number is growing very fast in the next picture right here. This tells you the pricing number for these fuels. Biomass range is very high. The green line is very wide, the green line, a green bar is very wide, because biomass is a function of which country you are using. Some countries, biomass grows very easily. Some countries do not. That's why the price changes. But on the average, globally, it's about 6 cents or so per kilowatt hour, globally. Geothermal, about the same, maybe 7.5 cents a kilowatt hour. Hydro is much cheaper, but 4.8 cents a kilowatt hour. Solar PV, not bad. Solar PV is about 8 cents a kilowatt hour. CSP, which is concentrated solar power, about 17, 18 cents. Offshore wind, 13 cents kilowatt hour. Onshore, 6 cents a kilowatt hour. You know, in the UK, Scotland has a lot of offshore projects ongoing today. Why is the cost of offshore double the cost of onshore? Because in the water, you need different structure, different infrastructure, bigger, deeper turbine towers, all of that. Cost is different. If I now compare some recent cost data globally now, how has the cost of energy come down globally over the last 9-10 years? Solar started at almost $300 per megawatt hour, or 35 cents a kilowatt hour, solar. It is now about 4 cents a kilowatt hour, right? 4 cents a kilowatt hour. Coal is about 10 cents overall. That's the comparison. You can decide what you want to build. Wind and solar have no CO2, coal has. Again, the prices is what it is here. Fine, we got that, we understand the problem, offer some solutions. What's the bottom line? First of all, the three options I'm showing you. If we are able to replace fossil fuel with renewables, electric power sector, we are in good shape. Nuclear will help. Nuclear has no methane or carbon dioxide or NOx. However, if we in the power industry are responsible and taking actions to reduce the fossil fuel consumption, on the other side of the screen, it showed you today 40% CO2 coming from transportation. If they remain where they are, would not help. So we have to see what can be done to reduce the dependence of your car on petroleum or liquid fuel. One solution is large-scale deployment of electric vehicles. Possible. But question remains, what is the source of the electricity that is running your electric vehicle? From coal, it is not as good as if it's from solar, let's say. Good. Now the question is, for young professionals, what you should focus on. I'm giving you 3 examples in different continents. On the upper left is Bangladesh. This is a river boat. That boat has a solar panel to give light inside the boat, which is a library. So they are not using kerosene lantern. They're using a solar panel-driven light bulb. That's Bangladesh, Asian context. In the middle is Morocco, which is Casablanca in Africa. They are replacing, or they're producing more and more, or providing more and more surface rail transportation. That's true in the UK and many countries. That cuts down on traffic, which is driven by gasoline on the road. On the right-hand side is agriculture. This is data from New York. This is called hydroponics, where you grow vegetable, leafy vegetable, indoors without any land, in this case, by matching the requirement of light, the moisture, fertilizer, and CO2 will give you custom-made vegetable that is not needing any soil, no land. Other value is these are usually done in downtown areas. That means you're not transporting the lettuce or cucumber from place 1,000 miles away and not burning diesel engine to bring the food to your neighborhood. That's what I'm saying. I would like to have the young generation understand these and encourage their neighborhoods to go into hydroponics as much as possible. People are making a lot of money doing this. Other question I get asked, well, I am in London, I'm doing this, somebody in a different country don't care. So what is the point? My point is be morally responsible, do your part, and then be an example to others. So then you can show them what can be done by hydroponics or solar panel or surface transportation, which is not gasoline based. There's examples. So this is the technical part of my talk. I'll take a couple of minutes to talk about IEEE as a seed going forward. As we are doing today, we are doing a lot of webinars, meetings, which is not face-to-face. So we have learned how to cooperate, collaborate, and becoming a big community. Like I'm here, you are in Europe, in the UK. That's very good. What I'm suggesting, as we come out of the COVID-19 pandemic, we'll not forget this experience. Let's keep that in mind, how we manage life without driving my car, without going to work, without burning fuel to go from place to place. We can do that. So this would, I hope, would be a lesson that we can take forward and do things in a more friendly to the way of environmental impact, more friendly ways. But for this to happen, we need to make IEEE broader, meaning it has to bring in many people who find IEEE relevant in their job. Could be an engineer in a factory which is making some gadgets. So they are using electricity. How can this engineer's life be made better by IEEE activities? Fine. Finally, in order for volunteers to feel they have ownership, they must participate in the governance. Governance doesn't mean only the IEEE board. Could be the board, could be committees at the board level, could be society governing boards, could be section leaders like you have here in UKRI, so that technologists and academics, all parts of the world feel IEEE is some place they can go and their voice will be heard. If I become president, I'll make sure that happens. Lastly, I see the numbers are good. Senior members is no limit. You can apply, have 3 references and get it. Like I just heard from Eduardo, UKRI has 1,333 senior members, end of June this year. Good number out of almost 9,000 members. If I compare that number with US numbers, I see US and Canada on a per member basis has more senior members than most of the other countries. Same thing applies to fellows. UK is good in fellows, but not all countries are equally blessed. So what I have done to help that situation, I've told PS chapters in many countries, please publish the names of your senior members and fellows on your chapter website. Why is that important? An engineer in a company, she thinks she can qualify, but she doesn't know 3 people to ask for references. If the names are published, she can go to the list and see, maybe she knows somebody already from the list, and maybe her boss knows somebody. That way, you break the ice, and they feel energized to apply for senior membership, which they can get if you get 3 good references. Fellows are more difficult because it has more checks and balances. They need 5 references, at least 3 to 5. Again, if you have the fellow list published on your section or chapter website, you'll get that young engineer or young professor more enthusiastic. So this is being done in my case with PES. I want to see it done globally all over IEEE. Now my last slide, again running for election, but point is not me. My urge to you is please go vote. Voting starts Monday next week, which is 17th of August. Go on through end of September, plenty of time. All of you who are members, voting members, will get an email from IEEE, the voting starts. Please click on it and you vote. Finally, I have a website about my research and the lectures I've given today and other times. My name, srahman.org. If you go there, you'll find this slide deck, many other topics I've worked on. Finally, for younger generation, I am on Facebook, I am on LinkedIn, I am on Twitter, and also YouTube. You can find me there as well. So with that, I'll stop my screen, Panos, stop sharing, go back to you. You can take over and start the next phase of this seminar.
Thank you very much for the very interesting presentation. I think we already have a few questions posted at the chat, so I can read the first one. And feel free in the meantime to ask, to type your questions in the chat or potentially raise your hands if you can, so that I can unmute you if you want to say something. So the first question is from Oli Bachmann. What are your thoughts on pushing for a hydrogen economy and hydrogen combustion engines for transportation? Right.
First of all, I was very optimistic 10, 12 years ago, hydrogen economy. I did a conference on that topic in Washington. That's called Hydrogen Economy Conference. I did that because we're pushing for fuel cell power plants, fuel cell cars. So if you hydrogen in a car, fuel cell will run, which is your hydrogen and oxygen based PEM fuel cells. But then battery has taken over this business today. We don't talk about fuel cell cars much, we talk about battery cars. However, the potential is very much there. The issue with hydrogen is combustible, it burns itself. So a lot of safety issues have to be taken into account in hydrogen fuel cars. And that is coming across quite well, but it'll take time. So answer is yes, but it will not happen very, very soon.
Thank you for the answer. So the next one is probably more of a comment, as it seems. So I'll just read it through. Feel free to read it as well, Professor, if you want, from the chat, because it's quite big, so it might take some time to digest. So to Stephen Browning mentions that to accommodate more variable renewables in electricity requires serious flexibility, including other sustainable low carbon generation in the mix, plus a seismic change to customer attitude as regards to time of use, especially with EV charge discharge, which has the capability to enable flexibility if managed and to seriously disrupt electricity delivery if not. And then there is a comment saying that the 18 gigawatts of GB metered wind plant was down to 215 megawatts yesterday morning as well.
That's a very good comment. I have another lecture who talks about exactly these issues. So you picked the wrong lecture for us.
Right. Probably, yeah.
So what I have said is very true. I said you cannot solve this flexibility or intermittency issues just by storage. It's too much flexibility. Like I said, 18 gigawatt became 215 megawatt. It's a huge drop, like a few hundred times drop. But that drop was not long lasting. It drops and goes back up again. So what I've said, in order to manage large scale penetration, renewables, you have to be able to manage your load as well. Historically, what I have done, we call it load-driven generation, meaning power company does load forecast 1 year, 5 year, 10 year ahead. Based on that forecast, they build power plant. That's forecast and power plant. It's fine. Now, the generation is flexible. You have solar, wind as an example. We have a new term, I call it generation-driven load. Generation changes, can you change the load to some extent, not all the way, so that you are not caught unprepared. So we have done work on demand response. You mentioned it briefly here, work on other devices like building energy storage. In fact, like you said here, the EV can be your source of supply. For example, I am going to work on my EV, charging in my garage downstairs, and 4 o'clock, and like you said, wind slows down, supply slows down. By that time, my car has been fully charged. If I can reverse it, so I can serve part of my building using the battery generated power, I don't depend on the wind as much. So we have to be very smart, very real-time reaction so that we can deal with some of that. Rest has to be done with storage. So you're right here, Stephen Browning. It needs some customer behavior change. That is very important. So I hope we can educate them and make sure they understand. Otherwise, what happens? Either you do not penetrate so much renewable or the price goes way up. So that's the other side. So thank you, good comment.
Good comment, I agree as well. So I don't see any other questions currently or someone else raising their hand. All right, so there's another question that came in. So from Oli again, so what do you think is the most promising and inexpensive energy storage for the future? Can it be produced at a high enough scale to achieve net carbon zero for a country?
Well, it'd be multiple mix, not one thing. Battery cost has come down significantly. I read in Economist magazine the other day, many companies are looking at million-mile battery, not 100,000 kilometer battery, million-mile battery. Chemistry is there. That means all these batteries, million-mile battery, a car has a 100,000-mile life. So what about the battery? That battery goes to secondary market. Meaning today I can buy in the US batteries which have been taken off electric vehicles. Cheaper battery. I put it in my garage and part of my house will be served from that option. So that's one inexpensive storage. Other could be, in my case, I showed example briefly, compressed air energy storage, but more likely it will be hydrogen storage from excess capacity available during off-peak hours. So the hydrogen can be stored and used to run fuel cells or can be used as combustion fuel. So if you look at 20 years from now, things will look very different, very different. So that otherwise we should look at that option and see what we can do to get there. It's not going to happen in 2025. It will happen in maybe 2030 and beyond. That's my expectation. Battery, hydrogen, primarily these two.
Maybe a short follow-on question for myself as well. So do you see maybe hydrogen playing a role in decarbonizing heating as well, heating load?
You mean use hydrogen for heat at the load?
Yes, or potentially transportation as well, because you've shown that this is a big part of the production of carbon dioxide. So potentially this could be partially helped by hydrogen.
possible. The problem is the following, Panos. Today we make hydrogen two ways. Or electrolysis, the water becomes H2 and O2, fine. But most of the time, we make hydrogen today using steam deformation. If you throw high steam to methane, literally CH4 and steam, it breaks down. You get hydrogen and CO2. Then this is not decarbonizing, you're making CO2 again. But that's how it's cheaper way to make today hydrogen, cheaper way, steam and reformation. So we have to looking at more electricity-based hydrogen production. And that would be, if you have like nighttime electricity, which is very, very not much use. I have seen data from Texas, from parts of Midwestern US, the nighttime power availability is more than they can use. That's why they cannot, very good point here. In the US, I know for a fact, in the US, there is a incentive to use wind power. If you sell wind power to the grid, you get about 2 cents per kilowatt hour back from the government, 2 cents a kilowatt hour from the government. At nighttime, you have a lot of wind. Large coal power plant, nuclear power plant has to run. Otherwise, they cannot be on tomorrow morning. So they run. Then wind power is excess. So what they do today, they sell the wind power to the grid at negative cost. Negative cost. If I sell to you, I'm the wind guy, you're the power company. I sell to you, Panos, I'll sell -1 cent, not zero, -1 cent. Why? I make 2 cents from the government. You give -1, I still have 1 cent left. Okay? The nuclear guys are hurting. They're also selling negative price. Nuclear power plants sell to me at the power company -2, -3 cents. This is the market is kind of deformed. So if you do a lot of storage, that problem is solved. So that's why storage comes in as in a big way. You're right.
Thank you. Thank you. Right. So I think there is again follow-on question from Oli talking about, so I've read information about sulfur redox flow batteries becoming very cheap. Will they become a possible energy storage medium, perhaps for load balancing on a distribution level? Yeah, that's a question.
That's a good question. The redox flow battery is highly researched today. It's not commercially available yet. The good thing is you are not limited to the battery size. What a battery size? You have a box. In that box, you put electrode and acid, like a lead acid battery. The box limits the size. You can put many boxes. But flow battery, your electrolyte is in a tank, literally. A bigger tank, a bigger capacity of energy. But it's not yet cost effective because the chemistry is not fully understood. So you're right, it's a possibility, but it's very cheap, possibly. How much we don't know yet. So you have to watch the market, in my judgment, next 3-4 years, see where it goes. Other is there are many kinds of batteries being looked at. Then you talk about there's some high temperature batteries, which are on the market, but not very safe always. So battery would be a big player in this market for sure.
Right, thank you very much for the response. So anyone else that has any questions? Again, if someone wants to speak, they can either raise their hand, or if they can't do it, just type it in the chat and we can unmute you. One of the co-hosts or myself, we can unmute you. So if you would like to speak, feel free to do so as well. Right.
One thing I can add, Panos, here just for a few seconds.
Of course.
We cannot make every country self-sufficient by domestic source only. It's not possible. US buys power from Canada today. Many countries in Africa are exchanging power among themselves. So if you have a lot of wind in your country at a given point in time, you cannot use it. You could sell it to another country using long distance transmission lines, then you are in good shape. I think this is happening today. Many countries are building power poles. Africa has 4 or 5 power poles today, exchanging power. We have power pole between US and Canada, US, Mexico. European, good example. All these countries are West Europe connected. So if you have a lot of wind and Germany has a lot of solar, it's a good point to make here. Germany has a lot of solar during daytime, a lot of solar. They're selling that solar at low cost to Switzerland. As a result, Swiss-based hydro plants are becoming ineffective, the big ones, the smaller ones, because they are not producing cheap enough. So that means the solar is more than the demand in Germany. They're not wasting it, selling it to somebody else who can use it. Another example, Denmark and Norway. Denmark wind capacity is more than the country's load at night. Total country's load is less than wind capacity. So what do? They sell the wind power to Norway, very low cost. Then Norway uses it and stop the water from flowing. Water is stored at night. And they use the Danish wind power to meet their country's load. Daytime, Denmark has no wind power extra. Norway will sell power back to Denmark if they need it. This is the global exchange of electricity, which makes it reliable and cheaper for everybody. So bottom line is, do not look at your country's border. We must be self-sufficient in the country. Look at the option to exchange diurnally, day and night, or seasonally from winter season to spring and fall and so on. That makes a lot of sense.
Absolutely, yes. So maybe a short follow-on question from myself as well. And probably this will bring us towards 7 p.m., which is our time for finishing up. So I was wondering if you think that the technical, let's say, constraints that current power systems, electrical power systems have, is a big game stopper, let's say, for towards decarbonization, or if do you believe that we are kind of on top of the problems and we are basically ready to generate the technology that is needed to overcome the technical issues of the power system itself, to be able to accommodate, for example, the electric vehicles or potential electrification of heating, because this is a discussion in other countries as well.
Decarbonization is a national level discussion. And then at national level, they can decide what is possible. Give an example in my neighborhood here. Where I work in a place called Arlington, there are schools which are zero net energy. They don't buy net zero for the whole year, net zero. How do they manage it? They have some solar rooftop, some battery, but they have used what is called ground-coupled heat pumps. They're using the heat from the underground water to run the heat pump. That made them net zero. That means low carbon community. So this is possible in some cases. So my answer is, let's have a national debate. What are the opportunities? Like a school, I said, net zero school. You said, Panos, the electric vehicle option, so that we can lay out the options and see who can contribute today, at what cost, and what government has to do to make it possible. Example, in the US government will give you 30% back in taxes if you build a solar PV rooftop unit. You spend $10,000, buy your solar rooftop, including the inverter, government gives you back $3,000 right away. You are spending $7,000 for your system, which takes about 4 years to pay back. Hawaii is even better. In Honolulu, if you have a house rooftop solar, US government gives you 30%, Hawaii government gives you 35% more on top of that. So 30 plus 35, 65%, 2/3 is given come back to you. So 10,000 expense, you are spending 3,500. So many homes are going solar today and not buying much power from the power grid. That's one way they are decarbonizing. So that discussion has to happen globally. I hope that makes sense.
Mm-hmm. Yes, thank you. And I think we have another question that came up. from Oli again, talking about offshore wind energy looks to become as cheap as onshore wind and PV in the near future. Tidal energy is also taking off. Is there any research into combining the two on one structure? So tidal and offshore wind.
Not really, because offshore wind is towers placed in the ocean some distance from the shore. Tidal power, you have to have literally a dam to hold the water when the tide is high, like Lawrence in France is a good example. And then when the tide is down, let the water go out. That's a hydro plant, literally. So if you can say you'll put a lot of wind turbines on the dam, which is holding the water back, then you don't need to drill into the ocean bed to make the wind turbine stable. So that is what you're thinking. It makes much sense. The problem is large wind turbines, like we have 6 megawatt we're building in Virginia today, which are 6 megawatt. They must be spread apart almost 1 kilometer from each other. 1 kilometer. The rule of thumb is the separation between two wind turbines should be 10 times the blade diameter. Blade diameter today is 100 meters or more. 100 times 10 is 1 kilometer. Your dam is not long enough to hold 200 such wind turbines. Small scale, yes, but not in large scale. So one question here from Stephen Browning. Life cycle cost is not right way to value a plant. I fully agree with you. Time series modeling determine the worth, cost, emission, fuel security, potential plant mix, noting there will be excess in salt plant with variable, renewable, and mix. That's all of that is true. That is why I say you look at the full cost, not the initial cost. The problem is psychology. Initial cost is high for wind, let's say, more than coal today, but overall it's cheaper. Who will pay the high cost to the developing country who doesn't have that much cash? So if it has been talked about in the context of global warming and climate change, that there will be a fund created to help developing countries to go into wind and solar with a higher initial cost so they can avoid building coal-fired power plant. You saw my data in the beginning. 75% coal is coming from Asia, China, India, and other developing countries, 75%. Because to them, coal is cheaper than other things. So yes, this is a good idea, but there must be a solution that can be equally acceptable.
Thank you. And I think there is, again, is more of a comment from Oli about the offshore renewable energy catapult, which he says they have been doing some work on bladed turbine tidal power. It's basically underwater versions of the wind turbines. So it's a specific design, I guess.
There is an example in New York City about 10 years ago. It's a windmill in the water, literally windmill in the water. They put the two bladed turbines in the Hudson River next to the New York City. Then they produced close to a megawatt and put that on the grid. But again, didn't last very long because the issue was the corrosion of the blade in the water and maintenance was the other issue. So it's a possibility. It hasn't taken off because of the maintenance issues, I guess. But that's a good thought. On paper, sounds pretty good.
Right. Well, I don't see any questions coming up, and I think we are already past our assigned time. So is there any last question remaining for Professor Rahman? So someone thanking, Oli? Yes, of course. So if there are no remaining questions, then I'd like to thank once again Professor Rahman for taking the time and giving us this very interesting talk. And thank you for answering all the questions as well and for engaging with the discussion. Yeah, so thank you very much for this talk.
Okay,
I think we
thank you very much, everybody.
conclude.
Enjoyed good questions. And I would hope that if you are interested I've given you my website. I have some data, some past presentations on other topics like came up earlier about the smart grid issue. Look it up, please. Look it up.
Thank you very much, Professor. Thank you.
Thank you. Thank you. Thank you.
Bye.
Bye-bye.
Once again, thank you very much and goodbye.
Bye-bye.
Have a good
Take care.
afternoon.
Take
Bye.
care.